Now, what is gravitation? If we take two masses, m1 and m2, which is separated by a distance r, then the force of attraction between m1 and m2 is given as a gravitational constant, multiplication of the two masses divided by square of the distance between them. What it means is, you take any two masses anywhere in the universe, on Earth, on Moon, wherever, they have a tendency to attract each other, and the force with which they attract is given by this formula. Okay. Now, if we define a potential of a point from a body at a distance r, like in this case, it is given as G m1 m2 by r with a minus sign. Okay. Now this force F is responsible for giving G at any place, because G is a force and which is given by this formula. Okay. Now let's see, can G vary? Let's say this is Earth and you are standing on the surface, then this formula will be applicable, where m will be mass of Earth, this will be mass of the body, and r will be radius of the Earth. Now what happens if we go away from Earth? Okay. Let us say we are at a point P, which is at a height h from the surface of Earth. Okay. Then what will be the force of attraction? Gravitational force. Gravitational force will be, again same thing, gravitational constant, mass of one body, mass of another body is, in our case, mass of Earth, divided by r square. But what will be r in this case? R will be taken from here to center of Earth, which will be r plus h. Okay. So if we say that this is our new gravitational force, is equal to if we do some mathematical manipulation, and if we take r square outside, this becomes 1 plus h by r. Now what is this? This was our original mg, like what we saw here. So this becomes our original mg, and this gets divided by 1 plus so what it means is G at a point which is at a distance of h from the surface of Earth is given as, sorry, this was not G dash. This is our original G. This is original G, which is as if the body is on the surface of Earth, divided by right. So as we go high and high, this G dash is going to become lesser and lesser. We have already seen how G varies when we go up. Now let's calculate what happens to G if we go underground. Let's see, this is our Earth. And now we dig a tunnel of height h. Now if we go h distance deep into the Earth, then what we do is we draw a circle of radius, which is, if this was r, this radius will be r minus h. Now what happens is, this portion of the Earth will not contribute toward the gravitation force. Only the inner portion of the Earth will contribute to the gravitational force. So we can find gravitational force is equal to R, in this case will be R minus h square. Now this m will not be full mass of the Earth. Instead, this will be this portion of the Earth into rho, which is the density, divided by. Now this becomes if we knock off, if we remove rho, then basically this becomes the cube root of the two radiuses. And if this was small m, this would have been. So the mass of this will be in the ratio of r minus h cube divided by r cube into m. M is the mass of the full Earth divided by. So this becomes G . Now if we split r cube into two portions, this becomes the original mg. This we can also write as mg naught minus h bar. This force was our mg. So our new G inside mines would be which means as we go deep into the mines, as we go deeper into the mine, this G dash becomes lesser and lesser. Now, is there any other way which can affect G? Yes, there is a way. There is another way. There is another very peculiar phenomena related to circular motion. We have our Earth here. Yes. And let us say there is a point P here. Now, since the Earth is rotating, will it have any effect on apparent gravitational force? Why? Why should it change? Yes, it can change because, as we have seen earlier, in a rotating body, in a uniform motion, there is always a centrifugal force acting radially outwards, centrifugal force, which is actually a pseudo force, which is acting outwards. And the magnitude of this centrifugal force will not be same everywhere because radius is changing everywhere. This angle theta is changing everywhere. Okay, so let's analyze it. Let's say there is a particle P which is making angle theta with the vertical. If this is making an angle theta, then we can say G dash, apparent G dash that we experience is G square minus omega square R, omega square R, sin square theta 2G omega minus R. This is the formula. Wherein this is a standard G, which doesn't change with position of the Earth or rotation. Omega is the angular speed at which the Earth is rotating. This one. Or rather, if you see it like this, it will be rotating like this. Then theta is this angle. So apparent gravitational pull is given by this formula, which it says that this will depend on our theta, the angle which it makes with the vertical, and omega. Omega we can consider to be constant. So theta is the only variable, which means we have some special, let's see some special case, and theta is 0. At poles, theta is 0 because you will be here. So the angle from the vertical is 0. If that is the case, then you will be left with g dash is equal to g square. This whole term will become 0, meaning thereby at pole you will have no effect. The apparent g will be same as actual g. Let's take another case. What happens at equator? At equator, theta will be 90 degrees because in that case you will be somewhere here and this theta will be 90. If theta is 90, then we know g dash will be g square minus omega square r. Sin square theta will become 1. And this will be equal to g minus omega square r. So apparent gravitational pull will be less at equators compared to standard G. Now let us find out the work done. Suppose these are two bodies, M1, M2. They are separated by a distance A. We know force of attraction is given by okay. Now, if this body travels dx distance from the original position, what is the work done? Work done will be FDR, which is equal to GM1 M2. For argument's sake, we write this as x square because A is the final value to which it gets integrated. So we are keeping this as x to distinguish it from this A. Okay. So this will be x square and it has moved a small distance dx. Now, if you want to find complete work done from going from, let us say, infinity to point A, this will be x goes from infinity to distance A. We are assuming that our starting point of this is not here but at infinity. And the reason is I will explain you once you get the formula. Okay. So this becomes GM1 M2 x minus 1 divided by minus 1, and x going from infinity to A. So this is x going from infinity to a. So this becomes so this is total work done in bringing one body from infinity to that point. And this term, which is the work done to bring this body from infinity to this distance a, is called potential energy. Which is now this potential energy is equal to what? Let's define another term called V is the potential multiplied by the weight of the body. So this becomes minus G1 if we take this as weight of Earth, this becomes this is potential. What is potential? Potential is the as this is an extension of this. What is potential? Potential is the capacity to create work and this is to be done by a unit mass. Capacity to create mass by a unit mass. If we multiply this by mass, what we get is potential energy, total potential energy. But if we talk about potential, potential is same thing, potential energy possessed by a unit mass, right? Now let us consider a sphere of radius r and there is a point P at a distance of r from here, r from the center. Now we try to calculate potential at this point as well as field at this point. So what we do is we make a table. We take type position of r, value of potential and value of E. E is the field, gravitational field. Okay. If our sphere is hollow, then and our R is, sorry, this we take as A to distinguish it from this R. If R is greater than A, that means it is outside the sphere. Then the potential is given by minus Gm by R. Okay. If R is less than A, means this R is less than A, which means that the point is inside this sphere. In that case, what will happen? Our potential will be minus Gm by A. Okay. Now we take another case. Now our sphere is not hollow, sphere is solid. Again, we'll repeat previous two cases. R is greater than A, means outside. Then our potential will be minus Gm summa and when R is less than A, that means the point is inside this sphere. In that case, our V is minus 3 Gm by 2A. How we get is a very laborious extended treatment. For the sake of simplicity, we are not talking about this. We are just giving the formula for it. So we have two cases when sphere is hollow and sphere is solid, and each we have two cases when the point is outside or the point is inside the sphere. These are the value of potentials. Now what happens to E? Our E is given as Gm by R square. Why is it so? Because if you take these 2 points, what is E? E is nothing but, this is actually gravitational field. And what is gravitational field? It is the force experienced by unit mass. So we are not multiplying it with MA because we are talking about unit mass. Otherwise, the formula is same as before. Okay. And now, if in a hollow sphere, we are inside the hollow sphere, then the potential is 0. This is very, very interesting. And you will see a similar treatment when you talk about static electricity. Exactly the same situation happened there also. Okay. Now, in case of solid sphere, when you are outside the sphere, your E will be again Gm by r square. And if you're inside, it is Gm r by aq. Again, we are not going into the derivation of this for the sake of simplicity. So this is the relationship of where the point is, what will be its potential, what will be its electric field, gravitational field, right? Kepler's law. There are three laws of Kepler. What is the first law? First law says that path of planets which are going about sun is not circular, but instead it is elliptical. If you take sun here and any point, any planet going about sun, then this path is not circular, rather it is elliptical. Okay. Now, had it been circular, had this path been circular, what would have happened? Let's say this is, suppose this was circular, suppose this was A, then this is the force of gravitational pull and this is the force of centrifugal force. Gravitational pull will attract it this way, centrifugal force will throw it out, will try to throw it out. And since it is in equilibrium, both will be equal. Okay. What is the second law? It says radius vector from sun to planet sweeps equal area in equal time. Let's draw is the major axis and our sun is here. This is our sun. This is our planet. And let us say the semi-major axis is A. Then suppose the planet is here at this moment. At some other point it goes here. The angle swept is, the area swept is this much. Okay. So it goes from P1 to P2. And let us say in the same time as it takes from going from P1 to P2, it goes to another point P3 in the same time. Then the area swept is this. What this law says, the area swept in equal times. In time t1, this is the area swept. In time 2, same time. T1 is same as T2. This is the area swept. This area and this area will be same. Okay. What is law 3? Law 3 says if a planet is going around sun, then its time period is proportional to this cube of semi-major axis. This is the third law. If you are sitting in a satellite going around in a circle, then again we have seen it before. There are two forces acting on you. One is the gravitational force, which will be and another will be centrifugal force. Now, since you are in an equilibrium state, these two will be equal, right? So, if we say if suppose you experience some normal reaction, then the net force that you experience is given by this force minus this force. Mind it, this is not gravitational force, is mv square by r. Why we have to make it equal? Because mathematically they are equal. If mathematically they are equal, then what happens to n? N is 0. N is 0 means you don't feel any weight. This is called weightless weightlessness. You don't feel any weight because of this fact. Because you are equally attracted by a gravitational force and counterbalanced by centrifugal force. So the net force is 0. Next topic is escape velocity. As the term escape means, escape here we are talking with respect to gravitational force. Suppose we are on Earth here. A satellite is shot up with initial velocity v0. Now, what should be the velocity of shooting it up so that it escapes from the influence of gravitational pull? Okay. What we do is we take energy, total energy of the satellite before and after firing. Before firing, it will be and suppose this is the final velocity which it attains. Suppose this goes from here up to this point, which is, let us say, at a height h from Earth. This is the radius of Earth minus right? Now, suppose this term is greater than 0. Then what happens is, if this is greater than 0, then obviously this is going to be greater than 0. If this is greater than or equal to 0, then obviously this term will be positive. This term being positive means u is greater than 0. Okay. So what happens is now, if we take this equation here, which means or V naught is equal to, if we cancel out m from both the sides, 2 gm over r. Now this is assuming this term became supposed to be 0. But what if it is not 0? If it is not 0, then our v, which is the final velocity, will not be 0, will be greater than 0. Which means that our satellite will keep going up and up. We have already defined what is field and potential. Just to reiterate, we defined again. Field is a force experienced by unit weight, unit mass. And what is potential? Is the work done to bring unit mass from infinity to that point, right? So field is a force, whereas potential is the energy possessed. Now, gravitational field, it is a vector because the force is a vector, is equal to total force experienced by the body divided by its weight, because we have seen that experienced by unit mass. Du shall be equal to minus dw minus m E dot dr. Okay. Change in potential is how much? Du by m for the unit weight, unit mass. Okay. Now, if we integrate these terms for the total distance from one place to another place, dv from, let us say, r1 to r2, this becomes R1 to R2. Okay. Now, as mentioned before, E may not necessarily be constant, it could be varying. So V so change in potential from going from one point to another point is integral of EdR integrated over initial place to final place.